Hi, this is Calculus 12, Chapter 5.2. This time we're going to be looking at definite integrals. We've looked at these functions. S of t is the displacement over time. V of t is velocity over time. A of t is acceleration over time. J of t is the jerk over time. And if we take the derivatives, we're going downwards. So derivative of S of t gives us V of t, derivative of V of t gives us A of t, derivative of A of t gives us J of t. So the question is, can we go the other way? And this is a loaded question. Yes, we can go the other way. This is the rationale for the fundamental theorem of calculus. So if we integrate J of t, we get A of t plus C. If we integrate A of t, we get V of t plus C. If we integrate V of t, we get S of t plus C. The definition of a definite integral. If f is a continuous function for the closed interval a to b, and we divide the interval a to b into n subintervals of equal width, therefore delta x is equal to b minus a over n, we let x0 equal a, x1, x2, and so forth of equal intervals until we get xn equals b, be the endpoints of these subintervals, and we let x1 star, x2 star, all the way to xn star be any sample point in these subintervals, so that xi star lies in the ith subinterval xi minus 1 to xi. Then the definite integral from a to b is integral from a to b f of x dx equals limit n goes to infinity, the summation of I equals 1 to n, f xi star times delta x. So here we say integral of f from a to b with respect to x. You could also say integral from a to b of f with respect to x. So you can change the order a little bit. And some points on notation. This fancy s is called the integral sign, f of x is called the integrand, a is called the lower limit of integration, b is the upper limit of integration, and together they're the limits of integration. Okay, if we wanted to take the left endpoint, we would have the same thing. Integral from a to b, f of x dx equals the limit as n goes to infinity, summation from I equals 1 to n, and here's where it differs a little bit, f of xi minus 1 times delta x. So this is our left rectangular approximation. Or we can take the right endpoint, integral from a to b of f of x dx equals limit n goes to infinity, summation from I equals 1 to n, f of xi times delta x. Okay, so if we look at just the first case, I is 1, I minus 1, so we're doing f of x 0. And at the last case, we have f of n minus 1. We have n partitions, and we have n plus 1 values, because we have x0 all the way to xn. And here, if we take the first case, we have f of x1, so we skip f of x0, and we go all the way to f of xn. And this is called your Riemann sum. And from our rectangular approximation calculations, we saw that the integrals converge to a single answer regardless of where we choose xi star, as long as n gets large. And please be aware we can integrate with different variables. We could do a to b, s of t, dt, or we could do something like integral a to b, f of u, du. Okay, so it doesn't always have to be x. Okay, so we have a function, we have a point A, we have a point B. Definition, area under the curve as a definite integral. Okay, so if y equals f of x is non-negative and integrable over a closed interval a to b, then the area under the curve of y equals f of x from a to b is the integral of f from a to b. So that's a lot of fancy words, but all we want to do is say this. Okay, so the area is the definite integral if it's non-negative. Remember, 0 is neither positive nor negative, so non-negative means 0 and positive. If you said positive, then that doesn't include 0. The next question you should ask is, what if y equals f of x is negative? Well, if it's negative, or actually it should be non-positive, then a equals minus the integral from a to b f of x dx, when f of x is less than or equal to 0. And of course, the next natural question is, what if y equals f of x is both positive and negative? So the area equals integral a to b absolute value of f of x dx. Or it's easier to think of it as area above minus the integral below x-axis. Okay? Or you can think of it as area above plus area below. Okay, so if you're using shapes, you would do this. If you're using definite integrals, you would use this. Okay, you must partition the interval a to b to properly calculate the area under the curve. And this means finding zeros. Okay, so if you're going to do the absolute value, you need to find out where it's positive and negative, and that means to partition by finding zeros. Let's go back just a little bit. So area under the curve is a bit of a misnomer. It really means area between curve and x-axis. It was originally called area under the curve because they originally looked at positive cases. They originally looked at positive functions. But when you deal with positive and negatives, it's really the area between the curve and the x-axis. And the term area under the curve just stuck. Okay, let's look at an example. Y equals x cubed. Find the area under the curve on the closed interval -1 to 1. So x cubed is less than 0 when x is less than 0. And x cubed is greater than 0 when x is greater than 0. Okay, so if we just look at this, this is x cubed. It's greater than 0 here. It's less than 0 here. So we have a partition. So integral from -1 to 1, x cubed dx equals minus the integral of -1 to 0, x cubed dx, plus the integral from 0 to 1 of x cubed dx. So we're doing the negative integral here because this gives us a negative value. Remember, area always needs to be positive, and here we're just taking the positive integral. Okay, so we're just doing a numerical example here, and we have minus -0.25 plus 0.25, and that gives us positive 0.5. Okay, so that's just giving you an overview of what we're trying to do. Evaluating constant function. So this will give us an exact value. We have our limits of integration, √2 to √18 of a constant value, √2. So we have √2, √2, √18. This forms a rectangle, and this will give us an exact value because it's a rectangle. We have length, we have width. So length times width, this is √18 minus √2 times √2. This gives us √36 minus 2. This is 6 minus 2, and that's 4. And that's an exact value. Here we have a line. We're evaluating from a to √3a of x dx. So here's a, here's √3a. And if we go across, this is a, and this is √3a. Okay, this shape is a sideways trapezoid. So we have B1, B2, and this is our height. And the formula for sideways trapezoid is B1 plus B2 over 2 times the height. So we have A plus √3a over 2, and we're multiplying by the height. So this is √3a minus a. And we have to FOIL this. So we have, this is a difference of squares. So we only have to do outer and inner. So inner gives us 3a squared. Outer gives us minus a squared over 2. This is 2a squared over 2, and that's just a squared. Okay, let's look at our next example. Compute the area of f of x equals 2 sine x plus x for the closed interval -3 to 2 using the left rectangular, middle rectangular, and right rectangular using n equals 10. Now, let's graph this first. We have 2 sine x plus x. And we'll need to make this smaller. And we'll just grab a screenshot of that. Okay, it's always best to just graph this out just to see what it looks like. So we have our 0 here. You do this graphically on your calculator. Okay, so it's 0. Because this is a trigonometric expression and this is a polynomial expression. And you can't do this algebraically very well. So you need to do it on your calculator. Okay, do that on your calculator. So we have -3 to 2. And in order to get an accurate answer, we would need to have constant delta x. We can't have a different delta x in this region and a different delta x in this region. So we take 2 minus -3 divided by 10. That's our delta x. We use the whole interval. So this is 5 over 10, which is a half. Okay, so this region, we have n1 equals 3 divided by 1/2. So this is 6. So we need a partition of 6 here. Here we have n2, that equals 2, the width of the partition, over 1/2. So we need to use 4 as our partition here. Okay, so our area equals integral -3 to 0, and it's a negative, and we'll have f of x dx plus the integral from 0 to 2, f of x dx, and n equals 6 here, n equals 4 here. So we go to our program, and we run our program. And we say 6 parts, and our left end is -3, and our right end is 0. Okay, so we have -8.48, and that's a minus. -8.52. LRAM, MRAM, RRAM, and -7.57. Let's round that up, 5.8 and 4.9. Okay, we'll run this again with the second part. And we have 0 to 2. 2.07. 4.86. 3.82. And we add those together. 10.56. 13.38. And 11.4. Okay, this is going to be different on the TI because of rounding errors. Okay, negative 9.22. Negative 8.52. Negative 7.58. $3.82, $4.86, 5.73. Okay, so don't worry about the calculators being different. I will mark it correctly when I look at your test. And let's compare this to the actual value. So we're going to calculate from negative 3 to 2. Calculate the whole thing. And we get, sorry, we're going to do this. Absolute value, bars, y bars, function, y1, x, and graph. Okay, we're going to do calc. The integral of the second one, you can see that here. And the lower limit is negative 3, and the upper limit is 2. So the actual is 13.31. So our most accurate answer happens to be the right rectangular approximation this time. So it's not always the middle one that's going to give you the accurate value. It depends on the symmetry of the function and the partitions. And that completes this lesson.